morning, Professor.
Okay. Let's get started then. Okay, the sun is quite bright today. Bit sunny. Should be okay. It'll go away pretty soon. So I'm going to talk about scattering of electromagnetic fields in this lecture, especially on Rayleigh scattering. Rayleigh scattering is an interesting topic, and it can be used to explain many phenomena that we observe in nature. So we start by studying the scattering by small particles, scattering cross-section. We briefly touch on small conductive particles, scattering, and then talk about optical theorem and so on. So what is Rayleigh scattering? It's actually a scattering solution of a small particle worked out by Lord Rayleigh many years ago, probably in the late 1800s or the early 1900s. Okay, so what we need to do then is to actually solve this problem. We actually need to solve this problem that we see here. And we assume that the particle is very small compared to wavelength. So we can solve this problem in closed form. That is, if you have an electrostatic field, and if you look for the scattered field outside E sub s, and looking for E sub I inside, those amplitude of the fields are given by these formulas over here, and you have worked this out in your homework or your exams and so on. And this is a boundary value problem. Okay, and when the particle size is very small compared to wavelength, we can actually use electrostatic theory to assume a solution or to arrive at a solution, and we can match boundary conditions to arrive at a solution and so on. So what happens then is that we are going to assume that the electric field is going to be given by the current. There will be induced current on the dipole. So when the current comes in, induces a dipole, or this particle looks like a small Hertzian dipole. Okay, it will look like a small Hertzian dipole. And if this electric field is time varying, going back and forth like this, then this dipole would also be time oscillating. And because it's time oscillating, it will radiate. And it will radiate like a small dipole and hence a Hertzian dipole. So radiate like a small or Hertzian dipole. A Hertzian dipole is just a small dipole. So the physics is quite simple. You have a time oscillating or time harmonic incident field, and this time harmonic incident field impinges on this particle, and it polarizes the particle, and you can solve for the amplitude of the polarized field inside and outside the particle using electrostatic theory and solving a boundary value problem. These coefficients, you have done so in your homework. But this field is time varying, so these amplitudes will also be time varying as a function of time, okay? So after you have solved for the current of the dipole, which can be approximated by that of a Hertzian dipole, so if JR is equal to that of a Hertzian dipole, which we have derived before, okay, the Hertzian dipole has a current distribution, looks something like this. And you can plug it into this radiation integral that we have derived before. A convolution of the Green's function with the current distribution gives rise to the vector potential. And when you plug this in, since this is a delta function, it has a shifting property. And that will just give you the value of R prime equal to 0. So you will take this function and set R prime equal to 0 because of the nature of the delta function. When you set R prime equal to 0, you obtain this expression. So that would be the field of the induced dipole, but we do not know what the dipole moment is or the current moment is. We have to solve for that. And we solve for that by solving the static problem that we have done in the homework. And once you have this vector potential, you can obtain the far field using this expression, or you can obtain the electric field using this expression. And that if you are in the vicinity of the particle, only this term is important because as we said before, if the particle is of a certain shape, the electromagnetic field has to contort itself so as to satisfy the boundary condition, and that the partial x, or the variation of the field with respect to space, has to vary on the order of the size of the particle, and hence this partial x has to have 1 over a dependence. The smaller the particle, the more rapid varying it is. So for the case of very small particle, this term starts to dominate, and this term starts to dominate over the other terms. Then you can say that the electric field in the vicinity of the particle would just be an electrostatic field. Okay, so this is essentially an electrostatic field. So knowing that the incident field, the field will be very much electrostatic in nature, then we can solve this problem to obtain for the polarization amplitude. And the polarization amplitude that we have obtained are given by these solutions over here. So are there any questions regarding the logic of solving this scattering problem? Okay, now we know what these polarization amplitudes are. Then we can use them to calculate the far field of this time oscillating dipole. So how do we do that? Let's talk about this in greater detail. So we know the amplitude of this dipole now. So in principle, we can find the potential due to this dipole. Then actually I did go through some math to show this derivation. And in order to arrive at this coefficients that we have shown in the previous slide, let me just go through the math a little bit to show how we can do that. And so I'm going to assume that we are close to the dipole, close to the scatterer. So it implies that I can use electrostatic theory to analyze this problem because I'm in a near field, and hence I can say that the scalar potential by Lorentz gauge is given by divergence of A over J omega mu epsilon. Okay, divergence of A times J omega mu epsilon. And then if I plug in the value for A that I have obtained in the previous slide, which is this case over here, the A that I have obtained, and then you can see that the scalar potential then is given by minus IL over J omega mu epsilon 1 over 4 pi partial Z times 1 over R e to the minus J beta R. Okay, why partial Z? Because A is proportional to Z hat times the constant, as you can see from the previous slide. Okay, so if you look at A, it is pointing in the Z hat direction, because when we plug in this current, A only has Z hat dependence. And so when you plug in A here, it will only pick up the partial Z, and then your scalar potential will look something like this. And you can work that out in greater detail. And most students will have problem finding this derivative. Okay, when we have something like this to differentiate, I find that many students have problem. What you need to do is actually to use a chain rule. The chain rule that allows you to change between spherical coordinates and Cartesian coordinates. So if you know this connection between spherical coordinates and Cartesian coordinates, then the differentiation of this then can be approximated by, let me see, something can be written as partial R, partial Z. Okay, we can write this derivative in this manner, and it's a lot easier to differentiate this expression with respect to R. And let me make an approximation that I'm in a near field. I'm in a near field so that beta R is much less than 1. And that hence when it differentiate this, the dominant variation is coming from here, because in the near field, this term is going to be small. The dependence on this term is going to be very weak. Or in other words, beta R is going to be very small. So then this would be just partial R, partial R, 1 over R. Okay, I'm going to have partial R, partial Z, partial R, and then when I differentiate this, then you will get this to be Z over R, 1 over R squared with a minus sign out front. Okay, because you can easily show that partial R is, if you take this, it would be half x squared plus y squared plus z squared minus half. And then when you differentiate with respect to z again, you get 2z. Okay, the 2 cancel, so you get this to be z over r. Okay, you can easily show that partial r or partial z is z over r. That's why you have this prefactor over here. But z over r is just equal to cosine theta. Because in the spherical coordinate system, z is r cosine theta. Then you can actually solve this problem assuming that the near field is going to be something of this nature, and you mesh boundary conditions. And as you mesh boundary conditions, you arrive at the fact that you have these coefficients, and we can go into a little bit of detail regarding that as well. So you can say that the field scattered due to this little dipole would be very similar to that, but you do not know what its amplitude is. So you put ES a cubed over r squared cosine theta. Okay, you're going to assume that the potential is going to be something like this, and if you work out this in greater detail, you find that if I plug this into here, I find that the potential due to the Hertzian dipole is actually given by minus I L over 4 pi epsilon r squared with the cosine theta. Let me see if I got this correct. That I have to divide by this j omega in the numerator. If I divide by j omega in the numerator, I notice that I omega, or this should be j omega QL. Okay, and if I plug that in, then this would be, there should be a j omega here in the numerator. And if I take care of that, then I should have an expression that looks like, let me see, the potential should be something like QL over 4 pi epsilon r cosine theta. Okay, that is a scalar potential that I will get if I were to plug it in here. Then what I do then is to mesh boundary condition inside the sphere and outside the sphere, and I will find that E sub s can be found by matching boundary condition on the surface of the sphere, and I assume that epsilon is epsilon outside, and then I have epsilon s on this inside the sphere. Then you can actually solve this boundary value problem and find that epsilon s is actually the epsilon s minus epsilon s plus 2 epsilon times E sub I, or E sub 0. Okay. Similarly, you can solve for the B coefficient inside the particle as well, which is the homework that you have done, and you can find that those solutions are given by this expressions over here. Okay. So we know how to solve for the problem of the polarization of this particle by an incident field, and it will have an amplitude that gives rise to this dipole moment, and that amplitude is given by this thing over here. Okay, then the next thing we can do is to plug this in to the previous expression, and then find the far field from this dipole. Okay. So the incident field induced a dipole. The dipole would radiate, and I will have to find the far field of this dipole. And the first thing I can do is actually to use this equation that the electric field is always given by j omega A minus gradient of phi, and that I can also use the fact that phi and A are related by the Lorentz gauge. So I also have the fact that divergence of A is minus j omega mu epsilon phi from the Lorentz gauge. And then I can rewrite this expression as to be j omega A minus 1 over j omega mu epsilon gradient of the divergence of A. Okay, so this is the relationship between the electric field and the vector potential A. And then I'm going to make a far field approximation in the sense that there'll be a dipole oscillating, but in the far field, a spherical wave that it produces becomes a local plane wave. Okay, it becomes a local plane wave. So if you're over here and observing this spherical wave coming out at you, it becomes like a local plane wave. And hence I can say that since it looks like a plane wave, then my del can be replaced with j beta. And if this is the r direction, then beta is essentially r hat beta. Okay, so the k vector or the beta vector, which is the wave vector of the wave propagating, is given by something that points in the r hat direction. And if you do that approximation to this expression, you will get that this is equal to j omega A. And then if you put in double del operator, and then you get the minus sign, and then you would have j omega mu epsilon beta square, okay, then r hat dot A. Okay, I will have something that looks like that. Okay, because I have let beta equal to that, and then when I plug in that, I get the two of them, and two of them will make this r hat dot A. And then I can write this as being equal to minus j omega A minus, and I can take this out. So if I take this out, then I would get something like 1 over omega square mu epsilon in the denominator with the beta square r hat dot A. Okay, but beta itself is just omega mu epsilon. You know what beta is. So these two terms actually cancel each other. And finally, you would have this being equal to minus j omega A minus r hat dot A. Okay, but what is r hat dot A? What happens is that r hat dot A, if A is expressed in terms of spherical coordinate system, it will consist of an r component, a theta component, and a phi component. Okay, so if you plug this in here, this would just become r hat A sub r. Okay, because it would just bring out this, it would just bring out this component, and then it would be subtracted from this A. A consists of all these three components, and finally, this becomes just minus j omega theta A theta plus phi A phi. So in the far field, okay, E, which is this expression over here, which is also this expression over here, becomes just that. In other words, the electric field due to a Hertzian dipole, which you have derived before, is polarized in the theta hat and the phi hat direction. And then in the case of the Hertzian dipole, you notice that A is given by this thing over here. Okay, if you go back to this slide, which is this slide over here. Okay, if you go back to this slide, remember that your A is polarized in the z-hat direction. So if A is polarized in the z-hat direction, it has no phi-hat component. Okay, if you convert this back to spherical coordinate system, you'll find that phi-hat is equal to 0. So because phi-hat is equal to 0, it will have only A theta and A R component. So if you were to go back to this slide again and express the far field, then the far field would be given by E would be equal to minus j omega theta A theta. Okay, A phi would be 0 since phi hat component is 0, because since A is pointing in the z direction only, A is pointing in the z direction only, as we see in our early derivation. Hence, the phi component is 0, then the far field would just be pointing in this direction. And you can actually look for the E H field, and then E theta over H phi would be related to each other by eta because they're plane wave. This is just a plane wave approximation. In other words, you have this Hertzian dipole. It is radiating out there. The electric field will be having only a theta component or theta hat component. And the H field, you can work it out in detail. You will only have an H phi component. Okay. The H field, let me draw it. This is phi hat. The H field would only have a phi hat component. You can work that out quite easily. And because of that, then you can actually work out the power that you have in the far field. And the power in the far field then is given by time average power is given by E theta H phi star. Okay, it is actually half the real part of this, but then you find that this quantity is always real. Okay, you can find the time average pointing vector out there, and you can work out your thing, and you essentially have your E field. E field is given by this, okay, and you already know what its amplitude should be, and then you can work out the H field, and you plug this in there, and then you can get the pointing vector. You can find that E theta would be equal to minus omega square mu epsilon. Let me see if I see this correctly. And if you write this out in detail, it will be given by epsilon s plus 2 epsilon a cubed over r squared e sub I. Okay. That is what E theta should be, and that is what we have. Okay, and there should be a cosine theta here, I believe. Okay, and then if you work this out, then the power scattered would be given by the Poynting vector integrating over all of angles. So it would be this thing multiplied by r squared sine theta d phi, and that would be integrating over 0 to 2 pi, 0 to pi, if you were to integrate over all of angles, okay? And then you can plug in this value of E theta H phi, and you can actually work this out quite easily. You will find that the power scattered is proportional to 4 pi over 3 eta epsilon s minus epsilon over epsilon s plus 2 epsilon. Okay, and then magnitude square, and then beta to the 4th power, a to the 6th power, and then E incident square. Okay, that's what you find the total power scattered would be, because you can perform this integration in closed form and you get this to be the power scattered. Okay, are there any questions so far regarding finding the total power scattered by this small particle? So it's a straightforward plugging and chugging. You plug in your E theta, plug in your H phi, and because it's related to each other by this one, so E theta, actually this will give you something like 1 over 2 eta E theta squared. Okay, because E theta and H phi are related by this number over here. Okay, and then when you plug in this value of E theta, you have to take magnitude square, so you get this term over here, and if you have to square this a cube, you become a6, and then you have something that looks like a beta square here, and there will be 2 of them. Okay, this is beta square, and then it will be beta to the 4th power because it's E square. Okay, and then you have EI magnitude square. The cosine theta will get integrated out because you have to square this quantity multiplied by sine theta, and then you can actually integrate that in closed form, and r square, this r square here, will cancel this r square, and finally you have something that is independent of r. Okay, then you can use this to define what we call the scattering cross section. The scattering cross section is defined to be an area. Is an area that if you multiply the incident field by the scattering cross section, okay, if you multiply the incident power by the scattering cross section, and that it will give you the power scattered. Okay, so this is the power scattered. This is incident power. To be more precise, this should be incident power density. So incident power density, which has the dimension of watts per meter square, multiplied by the scattering cross-section, give you the power scattered. Okay, and then you can actually define the scattering cross-section for this thing. And it is actually done in the lecture note. I wouldn't give you the formula for the scattering cross-section. You can derive it quite easily. But what we know is that the scattering cross-section is proportional to the frequency of the 4th power. Okay, what it says is that the higher the frequency, the more the scattering. It is one consequence of this analysis. Okay, so this is actually omega to the 4th power, if you want to look at this. And what Rayleigh scattering says is that the higher the frequency, the more the scattering. And it can be used to explain why the sky is blue. That's why I have this nice picture over here. and why the sky is blue. And then when you have the sunset, it has a red glow. Okay, we'll explain that using Rayleigh scattering. Rayleigh scattering says that the higher the frequency, the more the scattering. So if the sun is over yourself during noontime, the sunlight goes through a thin atmosphere, and the sunlight lights up the molecule, the water molecule in the air, okay, H2O molecules. And H2O molecules are very small, maybe half a nanometer. Sunlight lambda is about 400 nanometer if it's blue light, okay? So you can see that you can make a small particle approximation on the water molecule and estimate their scattering by using Rayleigh scattering. And what it says is that the higher the frequency, the more the scattering. So if the sunlight comes in, which is a solar spectrum, which is predominantly white light, the high frequency part will get scattered more than the low frequency part. So the atmosphere will only scatter the high frequency more than the low frequency. And when you look up in the sky, you see a blue sky because high frequency light gets scattered more. Okay, that explains why the sky is blue. Okay. And then we have to explain why the sunset is red. Okay. Again, the same thing applies here. What it says is that when the sun is very down low in the horizon, and if you observe the sunset, the sun ray has to go through a thicker atmosphere. So it has to go through a thicker atmosphere. So by the time the light ray reaches your eyes, all the high frequency components are being scattered away. Okay, so it removes high omega rays. Okay, it removes high frequency ray. So if you take the solar spectrum, take out the high frequency component of the sunlight, what is left behind is a low frequency component that reaches your eye, and those are the red light. So that's why when you are looking at the sunset, you see that it has a beautiful red glow because all the high frequency components have been removed. We can explain this using Rayleigh scattering. And also there's another physics that is quite interesting, which is that if you have an atmosphere and if the sunlight hits the atmosphere, okay, let me explain this. So say if the sunlight, the sun is here, and then you're down here, and there are water molecules in the air, in the cloud, or so on. The sunlight is randomly polarized. So the sunlight can be vertically polarized or horizontally polarized. It's random in either direction, okay? But then when it polarizes the water molecules, the water molecules are either horizontally polarized or vertically polarized. But you know that when you have a dipole like this, the radiation pattern of the dipole is like this, okay? It radiates predominantly in the broadside direction. It does not radiate in the end fire direction. So if you imagine these dipoles that are being polarized to be horizontal and vertical, and if you're down here, okay, you only will receive the radiation from the horizontally polarized light. Okay, so if you are able to use a polarizer like a crystal, some of this crystal used by the Vikings, it's called an Icelandic spar. You can actually filter the light so that you see only the horizontally polarized light and so on, and they will propagate in a different way. So by looking at the light scattered from the atmosphere, you can actually determine where the sun is, on this side, that side, or over on top of you by looking at the polarization of the light. And it was believed that that was how the Vikings were able to navigate themselves across the Atlantic Ocean to reach Iceland in ancient times, okay? Because they did not have the compass like the Chinese did in ancient time. So there is another kind of scattering, which is called Mie scattering. It's not Rayleigh scattering now. Mie scattering happens when the wavelength is on the order of the size of the particle. Then the analysis that we have done does not hold anymore. So what happens is that we observe the fact that if you did analysis by Rayleigh scattering, this cross-section, the scattering cross-section, grows as a function of frequency. And if you were to plot it on a log-log plot, you'll find that this becomes a straight line. So this power law, beta to the fourth, becomes a straight line. But it will not continue to be a straight line forever because this is a low frequency approximation. So Rayleigh scattering is only valid in the low frequency part. So you can say that over this part, we can use Rayleigh scattering. But we cannot use Rayleigh scattering when the size of the particle approaches that of the wavelength. The ratio here is actually over the projected area. This is the ratio of the monostatic radar cross-section. Radar cross-section is a kind of scattering cross-section, so it has a unit of area. Okay, and then you take the cross-section of a sphere and use that to be the projected area of a sphere. If you normalize these two, and as the frequency gets high, it is going to see this as a flat disk. That's why when the frequency gets very high, this ratio becomes 1. But when the frequency is low, the cross-section actually climbs very rapidly. And in order to predict the answer around this, where the wavelength is on the order of the size of the particle, you actually have to do Mie scattering. And Mie scattering is too complicated. It involves too much mathematics. And we will not do it as part of this course. You can read about it in Kong's book, if you want to read about it in Kong's book. Or my book. Okay, I also have a book called Waves and Fields in Inhomogeneous Media. I also talk about Mie scattering. So you have to really cross the dot the I's and cross the T's when you did those mathematics. But it can be done if you have the grit to do them. Okay, so but it has been done years ago by other people. Then the next thing I'd like to talk about is optical theorem. Optical theorem is the fact that when you have Rayleigh scattering, the wave comes in, induces a dipole. The dipole essentially scatters in all directions. Okay, so the scattering pattern of Rayleigh scattering is what we call isotropic. Okay, so we can say that this is isotropic scattering. Okay, and if you go to Mie scattering has no limit as to how the frequency should be. It can actually be used to compute the scattering cross-section of a particle or a sphere at increasingly high frequencies. And if it goes to some mid-frequency, you will find that most of the scattered energy gets directed into the forward direction. And if you go even higher in frequency, most of the energy is actually directed completely in the forward direction. Okay, And there's something called the optical theorem that says that once you know the scattering amplitude of the wave in this direction only, if you know how much power is being scattered in that direction only, you can figure out the total scattering cross-section of the object. Okay, so this is something I will not talk about in this course, but it's a good knowledge that you should be aware of. Only forward scattering is needed to know the total scattering cross-section. Okay, but it is not easy to prove, but I can give you an intuitive reason as to why this is true. Let's see if we can see this intuitively. So what happens is that when you have an object, when the wavelength is long, the energy gets scattered in all directions. Okay. However, if the wavelength is very, very short, okay, as you see in optics, the wave comes in and it might bounce off in some of this thing, but it will cast a shadow. It will cast a shadow behind the object. When the wavelength becomes very short and the frequency becomes very high. This is in the optical regime. Okay, this is in the optical regime, and this can be intuitively understood. And so what happens here? What happens is that if you think of this as the incident field, let me see that E incident plus E scattered is equal to E total. So over here, the two must cancel each other. In other words, E scattered must be equal to E incident in the shadow region. So in other words, it gives you the inkling that once you know the incident field and know what is being scattered in the forward direction, the scattering amplitude is such that they have to cancel each other in the shadow region. So knowing the scattered amplitude in the forward direction allows you to find the scattering cross-section of this object in all other directions. So this is why we have this fact that the higher the frequency, the more the power is being scattered in the forward direction. Okay, so actually this causes some puzzles to some students because I have them write numerical codes to calculate the scattering of an arbitrarily shaped object. And they were quite surprised to find that the higher the frequency, the more the forward scattering. The more the forward scattering is necessitated by the optical physics, that the power must scatter in the forward direction so as to cancel the incident field, making this shadow region having no field or zero field. Okay, and if that is the case, then you can intuitively feel that the optical theorem is correct. Okay, that is another way of looking at it, but there's another way of looking at it, which is something requiring more mathematical knowledge, which is that if you have a waveguide, we have learned about mode orthogonality, okay? And all the modes are orthogonal to each other. If they propagate in different directions, they are orthogonal to each other. There is something more powerful than that that we never talk about inside the waveguide. You can read about this thing in my lecture notes on field theory of guided waves, something called power orthogonality. Okay, power orthogonality, which says that all these modes would carry power that are orthogonal to each other, or that they carry power independent of each other. And by using power orthogonality principle in a waveguide, you can show that infinite space is nothing but a waveguide that is the separation of the two plates become infinitely large, and you can still apply power orthogonality to plane waves. Okay, you can show that different plane waves propagating in different directions actually carry power orthogonal to each other or independent of each other. Because of that, you can use this understanding to understand why only the power scattered in the forward direction can be used to predict the total power scattered by the whole object. Okay, I didn't say this in great detail, but you really have to go through the math to understand it. But that is another way you can understand why optical theorem is true. It actually follows from mode orthogonality and power orthogonality. Okay, I'll stop here. Do you have any questions? If no questions, I'll let you go, and thank you for coming.
Thank you, Professor.
Okay, thank you for showing up in class. It's always good to have people coming to class.
Thank you.
Professor.
Okay, I'll let you go then. Let me see. Bye-bye.